Okay, here's your next warm up. More of that quadratic practice. We're really going to try to get good at this. This first one we're looking at, and if you notice, it does look like it can factor. It should look kind of familiar to you. Hopefully you can do this by yourself. 1 and negative 15 won't work, and 3 and negative 5 will work. So we will change this question to x plus 3 and x minus 5 equal to 0, and we'll use a zero product property. One of those would have to equal 0 in order for it to equal 0 because they're being multiplied. So x can equal negative 3, or x could equal 5. On the second one, I'm going to go over the route of just getting x by itself. We're going to square root both sides. There's no reason to make it more complicated, and we get x plus 5 is plus or minus the square root of 24. You can break down square root of 24, and you should. So we'll change that to 4 times 6, which is 2 root 6. And then subtract 5 from both sides, and we'll get negative 5 plus or minus 2 square root of 6. And remember, that is two answers, negative 5 plus 2 root 6 and negative 5 minus 2 root 6. And what that means is they're just really nasty decimals where those x-intercepts or solutions are. Okay, back to the real stuff today. We are going to be solving systems of equations, and today we're going to use my favorite method, which is elimination. Okay, here's a review of what we did with graphing. Remember, when you have systems of equations, select all the possibilities for the number of solutions that you can have. You can have no solutions. They could be parallel. You could have one solution just like this where they touch. Can you have two solutions if you have two lines? There's no way you can make two lines touch in two spots. So that is not a possibility. And infinite would work because they could be on top of each other. And if you remember, this was called inconsistent. This was called independent and consistent. And this was called dependent and consistent. If parallel lines form a system, then they have how many solutions? They have no solutions because they do not touch anywhere. They have no points in common. By the end of this lesson today, you should be able to solve systems using elimination. Okay, most of us know this method, but why does it work? It works because we are going to be using properties of equality and adding the same number to both sides. But the same number that we're adding to both sides will be looking a little bit different. For example, if I say x plus 2 equals 5, I can add 5 to one side of an equation, and I can add x plus 2 to another side of the equation because x plus 2 is equal to 5. Yes, we know x equals 3, but I could add this guy or this guy. So when you're adding the two equations in elimination, what you're really doing is just adding the same number to both sides. So we're going to eliminate a variable, solve for the remaining, and figure out what that second variable would be, where those points would cross. And the thing you like to do is you like to find what's the easiest variable to eliminate, to get rid of. And if you have opposite coefficients, it's always the best. You always look for opposites. You always line it up first, make sure you have x, y equal number, and then look for opposites. Well, since negative 2x and 2x are opposites, I can easily eliminate them if I would add them together. So what I'm going to do is I draw a line and I just add all the columns. But again, what I'm really doing here is I'm really adding 4 to this side of the equation and adding 4 to this side of the equation. But the way that this 4 looks is 2x plus y. So that's why it's equal, and that's why it works. So negative 2x and 2x, those cancel or eliminated, and I get 4y equals negative 8. Divide by 4, and I get negative 2. That's the y value. Now, after you do that and you eliminate it, you need to find the last variable, the x variable. And you could pick your equation, whatever one you want. I always pick the one that looks easiest to me. So I'll go with the 2x plus y equals 4. And I know there are infinitely many points on this graph and infinitely many points on that graph. The point they have in common is y is negative 2. So to find the x value, we will just substitute that in. 2x plus negative 2 or minus 2 equals 4. Add 2 to both sides, and 2x equals 6, and x equals 3. So the point on the graphs, if I would graph them where they would intersect, would be 3, negative 2. How do you check it? You could substitute or plug it in. You could graph it, or you could use a calculator. I said I would try that, and I forgot to pull it up. Sorry, sorry. Now, the bad thing about a calculator is when you use it, you do have to get y by itself because the calculator wants um, everything in slope, intercept form to graph. So let's do some rewriting here. If I go back to my equations here. The second one's easy to get y by itself. You just subtract 2x. Oh, where's my pen? There it is. So y is negative 2x plus 4. The second one is a little bit trickier. I can add 2x to both sides, and I would get 3y is 2x minus 12. Divide all the friends by 3, and I would get y equals 2/3 x minus 4. Okay, so let's graph both of these into my graphing calculator so you can see what happens here. Okay, 2/3 x minus 4. So 2 divided by 3, x minus 4. That's your first equation. Your second equation would be negative 2x plus 4. And we can graph it. Oh, my zoom's all messed up. Zoom 6. Let's look at the standard zoom. Okay, so there's one equation. There's the other. Clear as day, there's the solution. Now, you could kind of guess where it is, but that is not a reliable method. Trace is a key that I highly recommend you do not use. You could go to the table and look and see if there's any points in common. And oh, sure enough, there it is, 3, -2, -2. So 3, -2 is the point of intersection. But the best thing to do is this command, second calculate. And we want to know where the graphs, oops, second calculate. I wanted to clear off the annotations so you can see what's happening here. We're looking for the intersection. Where do they cross? Where do they intersect? And you can graph as many graphs as you want on a graphing calculator. Now, we only have 2, but the reason it asks first curve, because it wants to know which 2 graphs do you want to know are intersecting. Well, I want to know where this blue graph, so I hit enter. It'll automatically jump to the second graph, hits the second graph, and I'll hit enter again. Now, some graphs hit more than one places, so that's why it's asking for the guess. They want to know which one do you want it to find, and I want it to find this one, and I get 3, -2. And I know I did it right. So graphing calculators can be used to help you check these. Okay, something special. Let's solve and classify these guys. So what happens here? First of all, nothing is even lined up. In order to do elimination, you have to have everything lined up. I like it in standard form just because that's how it usually is when you do these problems. But this guy is not. So we're going to do some rearranging here. I'm going to keep the 0.3x plus 0.4y equals 5. And I'm going to rearrange this so it's a negative 0.3x. I'm going to subtract the 0.4y. And then I'm going to move the 5 on the other side by subtraction, and that will equal -5. So what do I have? Well, I could do elimination, and I have opposite coefficients here. But if you notice, everything cancels out, and you get 0 equals 0, which is definitely true. But if I was really careful here and I would have divided everything by -1, you would have seen that they are the same equation. It is the same equation, which means that those lines are on top of each other and there are infinitely many solutions. What I like to tell myself is that if it's true, then there's solutions. And if everything's gone, it's just infinitely many solutions. And if there's infinitely many solutions, we know that's called a consistent graph because there is a solution and they are dependent because they are the same. How about these guys? They're all lined up for us and we already have the opposite coefficients, so we can add them up for elimination and you get 0 equals 7. Well, how do you feel about that? That is not true. And if it's not true, then there's no solution. These two graphs, if I got y all by itself, would in fact be parallel. And we know that parallel lines do not have a solution. They are called inconsistent. What if you don't have opposite coefficients? What can you do then? Well, you should always line up first. So let's go ahead and line up by moving this 2y over. So I have 3x minus 2y equals 10. And now I can see what I'm dealing with. Well, what you can do here is you can pick what you want to get rid of. What you're going to have to manipulate one of the equations. You can multiply to both sides of equations. You can add to both sides of equations. You can divide both sides of equations. We will use multiplication property to make opposites. So like I can see, well, y's have 1 plus 1 minus. So let's get rid of the y's. What can I turn a 5 and a 2 into so that they would be the same? Well, I could turn them into tens. If I multiply everything here by 2, I would get 8x plus 10y equals 88. If I multiply everything on the bottom one, how do I get it to negative 10? Because that's what I really want. I want negative 10y. I would just multiply everything by 5. And I would get 15x minus 10y equals 50. Add both equations, and then the y's are, in fact, eliminated. And you get 23x equals 88 plus 50, which is 138. Divide both sides by 23, and you get x equal to 6. Now we know what x is. Let's find y. Pick your favorite equation. Since the top one is the least marked up, I'll go ahead and plug that 6 in for x there, equals 2y plus 10. That would be 18 is 2y plus 10. Subtract 10 from both sides and you get 8 equals 2y. Divide by 2 and y is 4. X is 6, y is 4 means if I graph those two graphs, 6, 4 would be the point where they would intersect. So here are the formal steps. You align them, you multiply one or both, you eliminate, you solve, and you substitute, just like we just did. So let's practice this one when there is fractions. Fractions are yucky. I don't like them. So what can I do? Well, I can do whatever I want. I can change the way this looks first so I don't even have to look at the fraction. Let's multiply everything by 2 so I don't even have to look at that guy. Then I get 6x plus y equals 6. That's way better looking. And now when I look at the system of two equations, that's all ready for elimination because I have a minus y and a plus y. That would give me 12x equals 8. And I am going to get a fraction, it looks like, because 8 divided by 12 will, in fact, be a fraction of 2/3. So x equals 2/3. Now, what would y be? I could use the top one if I want, but I'm going to use the second one. 6 times 2/3 minus y equals 2. 6 divided by 3 is 2. 2 times 2 is 4. That's 4 minus y equals 2. If I add the y, subtract the 2, I get y equals 2. And these two equations will intersect at 2/3, 2. It does not have to be a lattice point. It could be a point that's in between. So what went wrong here? A student was solving a system of equations and he made some mistake. So here's what he had, and it looks like he did first. It looks like he wants to get rid of the x's. So it looks like he was multiplying everybody by 2. So he has the negative 2x. There's the 8. Oh, dogs. What did he not do? He didn't multiply the 13 by 2. You have to multiply both sides of the equation, not just the left side. Okay, can we write our own equations and solve them? What does that solution mean? A group of 2 adults and 4 children spent $38 on a ticket to museum. A group of 3 adults and 3 children spent $40.50. Looks like two facts to me. We are going to write a system of equations. A is an adult ticket, C is a child. This is a linear combination when they give you two facts like that. So I have two adults, and then I have 4 children. So 2 times the adults' tickets was 4 times the children's ticket, and that was 38. 3 times the adult and 3 times the children, that was $40.50. Don't have opposites, and I'm not even really close anywhere, so I can decide what I want to get rid of. Let's get rid of the A's. What can I turn a 2 and a 3 into? Well, I can turn it into a 6A, but this would have to be a minus 6A. So how can I turn the 2 into the 6A? I'll multiply everybody by 3. So that will be 6A, like I needed, plus 12C is 38 times 3, which is 114. Multiply the bottom. How did I get from 3 to negative 6? I'm going to multiply everybody by negative 2 this time. Be careful with your signs. Negative 6A. This will be minus 6C equals $40.50 times negative 2 is negative 81. This is the baddest part of my slate. I need to see if they can get me a new one. Add them together, and I get 6C is 114 minus 81, 33, and divide by 6, 5.5. So C is 5.5. I can find A by using the equation of my choice. I'll go ahead and use the top one. 2A plus 4 times 5.5, which I know is C, has to equal 38. So 4 times 5.5, that's 22. 38 minus 22 is 16. So 2A is 16, divide by 2, and A equals 8. So A is 8 and C is 5.5. Well, what does that mean? Go back. What was the A? A was the cost of the adult ticket, and C is the cost of the child's ticket. So knowing those two facts, we were able to figure out how much the tickets actually cost. Okay, one last example. I'm actually going to move this over here because of the dead spot in the board. One company charges a fee of $10 plus $4.50 an hour to rent a canoe. A second company is $12 plus $4.50 an hour. So this is an initial condition plus a rate of change, also a way you can write a line. They want to know when it will be equal. So what is the cost? The cost is going to be 10 plus 4.5 an hour for the first one. And the cost for the second one is 12 plus 4.5 an hour. Well, let's think about that for a minute. Do I even really need to do work here? Are they ever going to be the same? The rate of change is the same. It's always adding 4.5. Isn't this company always going to be $2 less than this company? Absolutely. There is no solution here. This is an inconsistent equation. The rate of change is constant, and they already started far apart, so they're never going to touch. That is an inconsistent solution. There is no solution. So in summary, here are the types of problems we have. This is all the notes highlighting you can put in your notebook, the types of problems, if they match, if they don't match. And what did we do? We solved problems by elimination.